Okay, so we're right at 1 o'clock, and so far we've got about 40 people in here, so I think we'll go ahead and get started. So welcome everyone to our third webinar in our series, Producing Robust Livestock Through Nutrition, Genetics, and Soil Health Management. So in our webinar series, Dr. Vanderlei put together that piece of nutrition. Then Dr. Woody Lane came in and he talked to us a bit about our pastures, our forage quality, and then of course put into place that piece of using a soil report. And today we have Dr. Jamie Corder, and she is going to be presenting on the genetics piece, selecting genetics for your desired phenotype. But before I introduce her, I just have a few housekeeping items. So first of all, each of these webinars is worth 1 continuing education credit for those of you who are registered professional animal scientists. Anyone who has attended the first 2 webinars, keep going, attend this one, attend the next one, and you will be qualified for a drawing for a free near-infrared spectroscopy forage report and some ward gear. If you have questions during Jamie's presentation, please ask them in the chat box or in the Q&A. And this webinar will be recorded, and we'll be sending you a link to that. And you can find this one as well as the previous ones on our Ward Laboratories YouTube channel. So now that we've got all of that out of the way, I will introduce our guest speaker today. So Jamie Corder is originally from North Carolina. She received her bachelor's degree in animal science from North Carolina State University. It was here that her passion for the beef industry began. Following graduation, she went on to obtain a master's degree in animal breeding and genetics from South Dakota State University. During her tenure there, she interacted with and learned from producers of all ages and background. Her thesis research was conducted at the United States Meat Animal Research Center in Clay Center, Nebraska. Working with leading geneticists to better understand calculations of EPDs, this knowledge and experience led her to the decision to attend the University of Nebraska-Lincoln for her doctoral degree, where she worked alongside Drs. Ron Lewis, Matthew Spangler, and Temple Grandin to better quantify docility for genetic evaluations. Following graduation, Jamie accepted a position as the beef product manager at Neogen and is excited to bring her passion and her experience to the beef industry while also absorbing years of knowledge from existing industry leaders to not only educate herself, others, but also utilize herself. So with that, I'll let you share your screen, Jamie, and you can jump right in. Thank you again for being here with us.
Yeah, no problem. Let's see if I want to figure this out. Okay.
All right, looks good.
All right, perfect. So yeah, thank you, Rebecca, for that wonderful introduction. I think I should have shortened it, but yeah, as she said, I'm very happy to be with you guys today. I truly have a passion for educating producers and others about the use of genomics in the beef industry. Specifically today, we thought it would be pretty informative to help discuss how we can specifically use genomics to select cattle to match a desired genotype. There we go. But before I get into the good stuff, we always have to talk about the history. And so people are sometimes surprised to know that the history of selection in animals, even based on phenotype, goes as far back as the 1700s. A man by the name of Sir Robert Bakewell actually created his own breed of sheep based on phenotypic selection and line breeding back in, like I said, the mid to late 1700s. And so that was even before the famous publication by Charles Darwin on the origin of species. So as we all know, within the famous Origin of Species, Darwin took the time to outline his ideas on natural selection and survival of the fittest. But what people, I think, sometimes don't know is that he was kind of the first person to ever discuss the idea of just basic phenotypic selection of animals, and that man has the power to do that and use variation within species to his benefit. And so the quote that you see on the screen basically says that. So nature gives us variations within animals, and then man can make decisions, mating and selection wise, to add them up in directions useful to him. And so in this sense, he can take one animal and make useful breeds. And within the beef industry, we've done that, right? All cattle, we didn't have 32 or 34 breeds of beef cattle from day one. We had probably one or two, and then they have attributed to the multitude that we see today. But another fun thing that I like to look at when we talk about how we've used phenotype to make selection decisions through the years is just the overall size of cattle, right? I mean, they say that we produce a multitude of the amount of beef that we used to with a much smaller amount of land mass, than prior. And so if we think about that just from a simple terms, we refer to them as buckle cattle, right? But back in the 1950s, I've shown you here on the left-hand side of the screen is an image of what a champion Angus and champion Hereford female would have been at a specific livestock show in the 1950s. Because back then, that was the phenotype that cattlemen found to be beneficial for their needs. And so they made the selection decisions based on that. And then as times changed, focus has changed. And, on the right-hand side of the screen is where we are today. Now, that Angus bull and that Hereford female there didn't come to be only through phenotypic selection, but overall you can see that man has made the breeding decisions that have changed the overall look and composition of the cattle. In addition to just man's ability to make artificial selection decisions, Gregor Mendel entered into the industry, around the same time and helped to define what we refer to today as basic laws of inheritance. So this is just the idea that, and for those of you who aren't familiar, Gregor Mendel was the guy with the famous pea experiments, right? So he made breeding decisions among pea plants for specific shape, size, and composition of the peas, and recognized mathematical patterns of inheritance as he made those decisions and measured the phenotype within the progeny. And from that, came two things: the mathematical patterns of inheritance, as well as this idea that genes are inherited in pairs, and you get one of each pair from each parent. This will be more important here in the next coming slides when we talk about basic inheritance of DNA. But I would be remiss if, as an animal breeder, I didn't at least give you a few equations. So the most basic of animal breeding equations is that an animal's phenotype is a combination of their genotype and the environment in which they're raised. So the phenotype is defined as any physical characteristic that we see, be it size, color, conformation, performance, you name it, that is a phenotype. It can be measured. The genotype, is their genetic merit or their predisposition for a trait of interest. And then the environment is everything that isn't included within the genotype. So that could be the nutrition that they're on, the environment in which they're raised, so how the weather was that year. It could be the aptitude of the AI tech if we're talking about something like fertility. It's basically everything that is not encompassed within the genetic predisposition of the animal. So back when we were first creating our animal, our estimates of breeding value, we had no way to know the true genotype. And so what geneticists then termed this estimation of breeding value was an EBV. Okay, and it's all based on mathematical equations and probabilities that I promise I won't get into here, but it's a culmination of the pedigree of the animal, so their sire and dam and who they're related to, and then the phenotypes as they're reported to the evaluation. So when we think about, how we the breeding value of an animal, the simplest way to do that is with a parent average, right? Because we know that calves inherit half of their DNA from their sire and half from their dam. So it makes sense that they would receive half of the breeding value from those animals. But to make it simpler or more complicated, depending on, your understanding of the topic, geneticists have also referred to half of the breeding value as what's called the expected progeny difference. So that is the value genetically that sire or dam is expected to pass down to their offspring. So because they only pass down half of their DNA, they only pass down half of their breeding value. But that is what's referred to as the EPD, or the progeny difference. And I think, the reason that it's termed, quote, progeny difference is because these values, as we see them printed in AI catalogs, on breed association websites, and bull sale catalogs, is that they're a deviation from the breed average. So they're trued up to 0. And so what that simply means is, let's say that a breed's average birth weight for a trait is 72 pounds. If a sire has an EPD of -1, then we would expect that progeny of that animal to be 1 pound below breed average across his entire calf crop. Okay. But in order to come up with that value, there's a lot of different pieces of information that come into play. So those include, like I said, the pedigree of the animal. So we need to know who the sire and dam is, but that's also who else he's related to amongst the rest. So who's his maternal granddam, maternal grandsire, all the way through half sibs and full sibs that are also reported to the evaluation. Then we include the phenotypes, not only of the animal himself, but of the animals which he's related to. And then as that bull gets mated and he has progeny hit the ground and phenotypes are reported on him or on those progeny, the progeny information then has an impact on the EPD of that sire as a whole. But I want to pose a question. So based on this information, the way a traditional EPD is calculated, today we have full sibling matings that occur as a part of embryo flushing in IVF and things like that. We have a lot of full sibling matings that hit an evaluation at the same time. So at the time that the animal's born, they have the same sire and dam, right? So therefore the phenotypes of their relatives are the same, and they have no progeny reported to the evaluation. So if I'm a seed stock Angus breeder and I flush my best Angus cow and then I mate her to, match those embryos with the best AI stud, in my opinion, for Angus cattle at the time, and then I implant those embryos among my herd, I want to be able to pick, the best bull that inherited the best genes from that mating in order, to sell, right? Because all in all, we think that a good bull mated to a good cow is going to produce good progeny. But at the time that these animals are born, from a genetic evaluation standpoint, they're equal. But we know that due to biology, that's not true, right? Not all offspring receive the same genes from their parents. And we know that that variability in phenotype isn't being accounted for in this type of evaluation. So to kind of help you wrap your mind around that, basic biology is, for all intents and purposes, variability, okay? And so it's referred to as this term Mendelian sampling. So in our embryo example, right, if we're talking about mating and matching a sperm together with an egg, calves have that mating results in 30 pairs of chromosomes. So within that fertilized zygote, there's 30 pairs of chromosomes. One of each of those pairs came from the sire and one came from the dam, or in other words, one came from the sperm and one came from the egg. But let's talk about the variability within that. So in one bull sperm, there could be all 30 of those chromosomes inherited from the paternal grandsire. There could be 29 from the paternal grandsire and 30 from the paternal granddam, all the way down to all 30 chromosomes from the paternal granddam. That's just a real fancy way of saying that within one specific bull sperm, because there are 30 pairs of chromosomes in an animal, there's over 1 billion possible combinations of chromosomal inheritance within one sperm. And then the same thing happens within the cow. So within one fertilized egg, there is 1 quintillion possible combinations that come from full siblings. Okay, so you would have to have at least 1 quintillion different full siblings to even have 2 that are genetically considered similar. That's the amount of variability that we talk about, that, you know, at the day an animal's born isn't accounted for when we calculate traditional EPDs. The power behind traditional EPDs is that as that animal's phenotype gets reported and as progeny records begin to be reported, then you see those full siblings deviate from each other. But the key to making genetic progress is the ability to make accurate decisions faster. And so we want to be able to do that, and we can do that faster with genetics. So there are many things that a DNA test can be used for to help us differentiate cattle past the phenotype that we see, so that help us solve that issue of full siblings aren't the same, right? And even half siblings to some extent. And the first and most easiest thing that came about as a result of, quote, DNA testing are things for simply inherited trait-specific genes. So those are something as simple, they're simply inherited. So there's one piece of DNA that codes for the phenotype. So that could be things like coat color and horn polled, or it could be some of the recessive lethal defects that have shown up in some of our beef breeds in recent years, where phenotypically there could be a cow or a bull in our herd that looks normal, that functions and appears normal, but they're a carrier for a recessive lethal defect. And when mated to a bull or a cow that also is a carrier, may present with calves that either die at birth or shortly after. And those are things, just like coat color and horn polled, that are important phenotypically that we want to be able to select. So some of you I'm going to take back to your classic, Genetics 101 course where we talk about using Punnett squares. But the reason that I'm including this is that Punnett squares have been around since Gregor Mendel. This is the result. These statistical probabilities have been around since the mid-1800s. And while I'm talking about coat color in cattle here, this is, basically what he applied to the phenotypic traits in the pea plants of his experiments. So within cattle, some people prefer black, some people prefer red, but in most breeds, both coat colors are possible, be it due to, mating with predominantly black breeds, or just due to the breed in general. So like Simmental, Limousin, Gelbvieh, all of those register red and black cattle. There's a American Hereford and a Black Hereford Association, but all in all, we want to be able to make decisions, informed decisions on what the expected coat color of our offspring are going to be. So as many of you know, the black color in cattle is dominant to red. So no matter how many copies of a black allele that an animal has, as long as they have one, they're going to be phenotypically black. So here in my example, I'm using the big B allele to represent the black gene, and the little b allele to represent the red one, okay? So if an animal has 2 copies of the big B allele, he's referred to as homozygous black, and he will be black. If he has 1 copy of each, he's heterozygous or a carrier. And so he has 1 copy of the red allele, but because black is dominant, he's phenotypically black. And then if an animal has 2 little b alleles, then they phenotypically will be red. So let's say that I'm a commercial producer and I've got maybe some red alleles in my herd that I don't know about because I've just kind of been mating, doing some crossbreeding and mating and not tracking the genotype status of my females. But I did open the bull cell catalog understanding that I bought my Simmental bull or my Sim Angus bull knowing that he was homozygous black, okay? So in order to estimate what I would expect the progeny of this mating to look like, I use a Punnett square. So for that, I take the allele status of the sire and I put it across the columns. So you'll notice now there's 2 B alleles on top of each column. And then I do the same thing with the dam, but it's across the rows. So you'll see there's a big B allele and a little B allele on the bottom row. And so then all I have to do is take my columns and drag them down, and then take my rows and drag them across. And by doing that, I look at the different possible combinations of allele status in the progeny. And statistically, even if I did 100 matings, I would expect, 2 out of 4 of those matings to be big B, and then another 2 out of 4 of those matings to be big B, little b. And so in this instance, all of my cells, even though they may genotypically carry a red allele, they are phenotypically black. So all of the calves from this mating would appear black. Okay, so I have 100% probability of having a black calf. But what if I'm a commercial producer and I don't track the genotype status of coat color in my females, and this time I'm using a herd bull that I raised myself? And I don't know it, but although he's phenotypically black, he's a carrier of a red allele. So in this instance, if I do, my sire across the columns and my dam across the rows, I fill in my Punnett square. It looks like this time, although I do have a 75% chance of having a black calf, there is that 25% chance that that animal will phenotypically have a red coat. And this is the same thing that can be applied to horn polled. It can be applied to any of the recessive lethal defects. It's the power behind the DNA testing is the ability to know the genotype status of your animals for a phenotype of interest and make educated mating decisions to manage and monitor that. So the second thing, and a little bit more complicated above that of trait-specific testing, is that of parentage. So what we do with parentage is similar to what you see on TV shows. So you send me the DNA sample of the sire and or the dam, you send me the DNA sample of the calf. And I can tell you that it is likely that this is the sire of that calf or it is not. But genomics has a lot of benefits behind identifying parentage. First and foremost, from a seed stock standpoint, we want to be able to verify that the pedigree that we're reporting back to the evaluation is accurate, right? We want to confirm that the sire that I'm reporting is the sire of this calf, that phenotype information that's reflected in his EPD is accurate. Most recently there was an issue with an Angus pedigree where I think it was the maternal grand dam was incorrectly reported, and that animal ended up being a carrier for a defect and had a lot of progeny before they figured that out. So whether we're correctly identifying parentage from a seed stock standpoint or, from a commercial standpoint, I think there's a lot of economic advantage to such a type of testing. And so on the graph that you see here, this is real life data from someone who ran parentage in a multi-sire pasture situation. So there's 8 bulls here. Each bar represents a specific bull, and then the height of that bar represents the number of progeny that bull in a single calf crop. And so the ability to understand what's going on in multi-sire pastures has a lot of different benefits, be it the ability to identify what bulls are having the most or the least calves. Maybe there's a dominance issue within one of your pastures, and in this instance, 407 and 504 would better benefit from being put in a pasture with maybe a less dominant bull. Or you can identify sires who may be causing either dystocia problems or maybe some abnormalities or some defects that you weren't necessarily tracking within your herd. You could trace them all back to a single sire. Or on the flip side of that, what if there's a bunch of heifers that a commercial producer really likes? He likes the way they look, he likes the way they perform, growth-wise, he decided to keep them as replacements. Maybe they can all track back to 1 or 2 sires with which, maybe maybe he's someone that you would consider keeping around a little bit longer than normal, right? But overall, not knowing the parentage of your calf crop may have a little bit more of an economic importance than a commercial customer would know. And parentage is a way to provide insight into the breeding schematics of multi-sire pastures that they wouldn't necessarily have had before. And then last but not least, and what we'll probably spend the rest of our time today talking about, is how DNA testing is incorporated into genetic evaluations from a seed stock standpoint, and then how we can utilize this technology in the commercial heifer replacement decisions. So this slide here should look familiar, except this time where an EPD only incorporates the pedigree, the phenotype, and the progeny information. Now we're incorporating the genotype. Okay, so with that final piece of information, we make the step up from a traditional phenotypic EPD into that genomically enhanced EPD. A lot of times, how those traits are reported through the association can be complicated. Okay, so they all have their own abbreviation. They're all reported on a different table. And in all honesty, there's a lot of different numbers that could be confusing. And so I've taken this information from the American Angus Association website on a specific bull that I just randomly chose to show you how this information can be reported to either the seed stock or the commercial bull buying customer. And so in this instance, I'm going to talk specifically about the numbers in white. So the top number in white is the EPD for that trait, reported as a deviation from breed average. So if we take the birth weight trait in this example, so the second column, you'll notice that this bull is +1 pounds for birth weight. So going back to my example, if the Angus breed, and I don't know this for sure, but if the Angus breed averages 72 pounds for birth weight, then we would expect that this bull's progeny would be 73 pounds on average, okay? And that is referred to as the EPD, or the expected progeny difference. The number on the bottom, in my opinion, is just another way of viewing that value. So the number on the bottom is the percent rank of that animal within the breed as a whole. In this instance, it's how this bull compares to the Angus breed as a whole. So for birth weight, this bull ranks in the top 40% of the breed. So that means that for this specific trait, he is slightly above average for birth weight, okay? And so if someone is, a little bit overwhelmed looking at the numbers, I always say that the EPD is the true number of importance here, because that's what's going to give you the expected phenotype of the animal. But if you're kind of new to EPDs and you're not sure what's considered good or not, then the percentile rank at the bottom helps you know, oh, this animal or this number is really good for this specific trait, or it's not good, right? And so you can help make your decisions accordingly. But likely most important when we're looking at these numbers is the one in the middle, okay? So that is referred to as the accuracy of the prediction. So any time that we make a prediction about something, right, we could either be really good or we could be really bad. And that is reflected in the accuracy. And I guess I shouldn't say good or bad, I should say confident or less confident. So the higher the accuracy of the prediction, the more confident that we are that what we're estimating is the true breeding value of that animal. Because remember, without knowing the whole genome sequence of an individual animal, we have no way of knowing the true genetic merit of that animal for a specific trait. What we're doing is we're making an informed and educated decision, an estimate of the breeding value of that animal based on the information that's available to us at the time. So what you'll notice is that as more information becomes available on an animal, right? So, from a yearling to a second-year bull to 3 years, the more information we have, as more progeny information comes in, you'll notice that accuracy will increase, meaning that we have more information in the evaluation and we're more confident in the, prediction that we're making. On that note, there's 3 reasons why seed stock producers genomically test bulls. And this may not come as a surprise, but the most important reason is that increase in accuracy. So not only are we moving away from those parent averages that I referred to before, where full siblings appear the same, but genetically they're different, the genomic information allows us to get into those differences on a molecular level and say, this full sibling inherited this good piece of DNA from the sire, while this one kind of missed out on that. So maybe they are, expected to be a little bit genetically different from each other, even though they're full siblings. This also allows us to make more confident selection decisions. So with increased accuracy, we're more confident in selecting a bull, say he's a Cavingese bull, we're more confident in selecting him and bringing him down and breeding him to heifers, knowing that the estimate of the EPD of that animal is as accurate as possible. And that really gets into what I refer to as risk management and customer service for commercial customers. So as a seed stock breeder, in my opinion, the main goal and objective should be to provide your commercial bull buyers with bulls that match their breeding needs and have the most accurate estimate of genetic merit as possible. So a lot of times the frustrations that I'll hear back is that I bought this really great yearling bull and he wasn't genomically tested. And then as more information came into the evaluation, his EPD may have shifted a little bit. So if I bought an animal for his low birth weight, maybe that birth weight increased or maybe it decreased, right? Because it's an estimate, there's a 50-50% chance that it's going to move one way or the other. But in my opinion, accuracy is more evenly equated to risk management, in that as you increase the accuracy, that movement in EPD potential movement becomes less and less. Okay, so as a commercial producer, I can go to a bull sale and buy a Cavingese bull and be confident that I'm going to take him home for 4 or 5 years and he's going to remain a Cavingese bull. And then because of that, from a seed stock standpoint, if I have more accurate EPDs, I can then make more accurate and confident decisions and make faster genetic progress because I'm turning over my genetics faster. I don't have to wait until a bull is 3 or 4 years old to prove himself to keep mating him. I can know when he's a yearling or 2 years old that this is a bull that I want to invest in furthering his DNA in my herd. So by doing that, I'm turning over the genetics faster and I'm decreasing the generation interval within my herd. And then last but not least, it allows for more accurate evaluation of traits that are either difficult to measure, like residual feed intake or dry matter intake, or are measured later in life. So stability, pregnancy, carcass traits, and things like that. So these are traits that are either difficult or are expensive to measure, or aren't measured until phenotypically reported back to an evaluation until way later in that animal's life, when they've already contributed substantial amounts of genetics to my herd, and I've kind of already invested in propagating that DNA, right? And so the ability to run a genomic test adds information to the evaluation where these traits become more accurate at a younger age. So I know early on if this animal, does have high EPDs for heifer pregnancy and carcass traits, whereas otherwise it would have taken me quite a while to get that phenotypic information reported back to the evaluation. All of that complicated stuff just to say that doing genomic testing on seed stock animals leads to genetic gain. So in this example, I'm talking about heifer pregnancy, and what we've done here is we've simulated the overall increase in average EPD for heifer pregnancy from 2014 to 2024, comparing just the use of conventional EPDs without genomics to genomically enhanced EPDs. So you'll notice that the benefit of that greater selection accuracy allows me to make confident, accurate decisions on what my breeding stock is at a younger age. And because of that genetic turnover and just the ability to make more accurate decisions, you see that faster rate of genetic progress over time. So I talked a lot about animal, why we genomically test, and I really wanted to do that to kind of set the baseline for the rest of the conversation. And so I hope that for the remainder of this, we can talk about how genomics and genetically tested animals can be used, and the results of that information can be used to select animals that match the desired phenotype. Okay, so a lot of times I get asked from both commercial and seed stock producers, it's an expensive technology, you know, it's a lot of money for me to invest in. How do I make the most return on the investment? What's my return on the investment? And my first question that I always ask them is, well, what are your breeding objectives, right? What have you set an overall goal for your operation to match your management decisions to that will help you make the most benefit from the investment in the technology? And unfortunately, sometimes they'll look at me and they'll say, well, I don't know what a breeding objective is. And so to help delineate what a breeding objective can be, you know, the first and biggest question is always, well, what's your revenue generation? What is your overall management scheme, and how are you making money, right? Because at the end of the day, cows are cute and I love them, but in order to keep doing it, we have to be profitable. And so as a commercial producer, are you just a cow-calf guy who raises cows all year, you know, has a fall and or a spring calving herd, and you sell them at weaning, you know, at around 7 months of age? If that's your biggest revenue generation, then it's weaning weight, right? Or do you background your calves for your calves for a little bit longer, and maybe put them on grass, you've got a little bit extra, and then you sell them into the feedlot when they're about a year old? Or do you have a relationship or the ability to retain ownership in the feedlot, and you sell based on weight and carcass composition, you know, at slaughter? From a commercial standpoint, those are kind of the three main pieces where I see revenue generation. But from a seed stock standpoint, you know, do you make your revenue based on bull and replacement heifer sales, right? And if that's your goal, then the more important question is, how do your commercial customers make money? What are the traits that they come to you looking for in their bull and replacement heifer decisions, right? And so at the end of the day, it's all about what traits match the needs of your revenue generation. But then secondary to that, there's probably other traits that a cattleman deems important. In my opinion, one of the most important is docility, right? Am I running these cattle around my children? Am I working cattle around children where, you know, I want more docile animals? Or am I running cows in the middle of nowhere where they have to be able to protect their herd, they have to be able to protect their calves, and I only see them twice a year? You know, maybe docility is not as important to you, and then you want a little bit more maternal defensive aggression in your calves, right? You know, what about mature cow size and feed efficiency? Do you monitor the mature cow size in your herd? And do you monitor what they're eating and how much they're eating for what they're making you? And those two things have to match the environment, right? What is the environment that you're raising these cattle in, and how can you, at the end of the day, develop a cow herd that excels in that environment? And so how can you use the traits and the genomics to select cattle to match that environment? And then finally, and equally as important, what phenotypes are critically important to match all of these needs before? And how can genomics be used to assist in obtaining these goals? And I always get kickback at that point, and they say, well, you know, genomics is the one and done. It's the only thing I should be using. And my answer is absolutely not. Genomics should be seen as additional tool in your tool belt, along with AI, along with nutrition, along with other management, to help a producer make more informed decisions that match all of the breeding objectives that they've established for themselves. And so genomics isn't the end all be all, but it's another tool that's available to help producers gain insight into the genetic composition of their cattle to help them, at the end of the day, make more money, right? So before I move into my examples, I wanted to first go over a little bit of the trait definitions that I'll be talking about. I took these directly from the American Angus Association website, but I think it's important when we have producers or anyone who starts to look at making bull buying decisions that they understand the traits that they're looking at. And so these again are from the American Angus Association, but the overall trait availability and definitions are going to vary from association to association. So from a maternal standpoint, we have things like calving ease direct and birth weight that are actually in an inverse relationship with each other. So the higher the calving ease of an animal, we would expect the lower the birth weight because they are negatively associated. And that makes sense, right? A lower birth weight animal is expected to have higher calving. Then we have traits like weaning weight and yearling weight that are expressed in pounds. And then from a feed efficiency standpoint, the Angus Association offers residual average daily gain and dry matter intake. These are mostly done via phenotypes reported through GrowSafe systems and things like that. But it's important to understand that these EPDs are based off of a constant amount of feed and at the feed that matches the overall need of the animal. And so, nutrition does align with the overall recording of these phenotypes, and that we have to have both of them to have success in our estimate. Then, from the maternal side, there's things like docility, heifer pregnancy. A lot of times people think that maternal milk is the pounds of milk that is produced by the cow, and that's not true. So for most associations, what maternal milk is the actual increased weaning weight of the calf that's attributed to not only the dam's milk quality, but also her overall mothering ability. And so that is something that I do like to point out, that it's not just pounds of milk produced in the female, it's the increased weaning weight in the calf as a subsequent effect of that, and then her overall mothering ability. Then from a cow requirement standpoint, there is mature weight and mature height. And then what I think sometimes gets overlooked is the cow energy value. So this is actually an economic EPD where it's expressed in the dollar savings per cow per year. So in this instance, a higher dollar energy EPD would mean that this cow is going to save you more money year over year as compared to one with a lower value. And then on the carcass side, there's things like carcass weight marbling and ribeye area. So in my example, and this is going to be a little bit long-winded, but I wanted to kind of walk you through how I would see selection of different bulls based on a desired phenotype. So I've got two breeding objectives. The first one is one that is really kind of common here in the Sandhills of Nebraska, where the biggest revenue generation is the commercial cow-calf producer who raises his own replacements and sells calves at weaning, right? And so from that standpoint, the biggest revenue generation would be weaning weight, as well as you want to make sure you're selecting replacement females with increased fertility and longevity that are going to make it that 6 years to pay for themselves and then some to start making you money. Other traits in this example that would be important would be mature cow size and overall efficiency of the animal, because the stocking rates in the Sandhills of Nebraska aren't necessarily the same as those in southeast Nebraska, where we've got a little more grass cover. And then also, in this instance, I'm a commercial producer who thinks calving ease is very important. I don't want to be out in my spring calving herd in the middle of March in a snowstorm pulling calves. And then docility is also one that is important here. So phenotypes that are critically important to match these needs, overall body composition and structure is important because the animal's got to walk a long way to get to water and feed. Overall udder composition is a producer, I'm just saying, to me would be important. And then lineage. And what I mean by lineage is there is nothing wrong with this, because we know that most traits are heritable, and that I'm going to select replacement heifers based on how their mom performed, right? Based on what I know about their dam. And that lineage does play a lot into the selection decisions that I make. So while genomics can be used in kind of that phenotypically important trait standpoint, the calves have to be on the ground in order for me to be able to look at them and make those selection decisions. It should still be taken into consideration at the end of the day, right? But on the top three, right? So what's the biggest revenue generation, what other traits are important, and what environment are they in? Genomics can be used to help obtain the goals and objectives that a commercial producer has set out for themselves. So for this, I just happen to have GenX's fall catalog laying around, and I went in and I selected 2 bulls that I wanted to compare. So Iconic and Converse were the 2 that I selected. So in this instance, I went on to the Angus Association and I looked up their EPDs, okay? And so these are the traits that, the EPDs that align with the traits that I need in my bull. And so what we can see here is that this animal, this bull here isn't necessarily a calving ease bull, right? His birth weight EPD is plus 1.6, calving ease is plus 7. So he's a bit, you know, below average in terms of birth weight. We kind of want a lower birth weight animal. But on the same coin, right, his weaning weight EPD is plus 95 pounds. So I would expect his progeny on average to weigh 95 pounds heavier than the breed average, which is a substantial amount. But because of that high weaning weight, it also seems like he has consistently high growth EPDs, and that his mature weight and his mature height EPDs are definitely higher than what we would want for a moderate framed cow, right, when we're selecting replacements. And even further than that, his dollar energy EPD is negative 55. So that means that any females that I kept out of him, I would expect to cost me $55 more than breed average every year, okay? So even though he has some really good growth in his weaning weight EPD, that doesn't necessarily reflect in what I would refer to as a moderate framed efficient cow, okay? But, you know, on the other side, his docility EPD is good. He's in the top 15% of the breed. And his heifer pregnancy EPD is okay, right? A plus 11.7 pounds. He's in the top 45% of the breed for that. So if we look at the other bull that I pulled out on Converse, it's almost the complete opposite. So very good numbers for calving ease. We're looking at an animal that's negative 1.7 pounds for birth weight, plus 16% for calving ease. So overall, I would rank him as a good calving ease bull. But the low birth weight also reflects in a moderate weaning weight, right? So he's plus 54 pounds on weaning weight, which is an okay weaning weight. Maybe, you know, if I am making my revenue based on pounds, I would want something a little bit higher. But what's really drawing me to this bull is his mature weight, mature height, and dollar energy EPDs, right? So he does have that lower mature weight and mature height that would lean more toward a moderate framed animal. And more importantly than that, his dollar energy EPD is plus 3. So I would expect to get $3 return on my investment for per cow per year that I kept from him as a replacement. Docility EPDs in the top 30% of the breed, I think that's a great intermediate optimum to stick around. The real only negative that I see for this bull is his heifer pregnancy EPD. So at plus 7.1, he is in the bottom 10% of the breed for heifer pregnancy, but based on the other pluses that I see in this bull, you know, I still would strongly consider him if these were the breeding objectives of my operation. So that was a lot, right? We just went through a lot of numbers that tend to get confusing sometimes. And so if someone's just getting into EPDs in general, I tend to push them more towards indexes. So what I mean by that is Angus just released what they are calling the $M or the dollar maternal index. And what that is it's a summation of the information that you see here. So instead of looking at a plethora of EPDs and trying to wrap your head around everything that's going on, it sums it into a single number value. And so in this instance, this represents the overall maternal merit of a bull, and that the value that his cows would bring to a commercial producer as replacements for the traits that you see here. And so it makes sense then that the one on the left, so the $M that's at plus 54, would belong to the bull on top, because too iconic, because in my opinion, he's not necessarily, that much of a maternal bull. He definitely has a lot more of those carcass traits that you're looking for. While this converse animal has a $M of plus 75. He actually ranks in the top 10% of the breed for this maternal index. So in this example, if these were my breeding objectives, that's the way that I would go about selecting a bull based on EPDs that match the environment and the breeding objectives that I have. But I put a question mark over that pregnancy EPD because it's important to kind of base those pros and cons accordingly. In the same example, what I'm looking at here is what's for breeding objective example 2 is completely the opposite. So here the biggest revenue generation is the commercial cow-calf producer who retains ownership and sells into a feedlot. So to him, other traits of importance are efficiency and carcass merit. He's actually located in Kentucky, so he's not worried about grass. And other phenotypes that are important, again, are body composition, structure, and lineage. So looking at the same two bulls, what we're looking at now are traits like weaning weight, yearling weight, average daily gain, and then their carcass traits of carcass weight, marbling, ribeye area, and then feed efficiency and dry matter intake. And so again, I'm not going to walk through, because of time, all of the traits that we see here, but again, summarized into what we refer to as a $B index. So what you can see here is that converse, or the bull on the bottom, results in about a plus $120 beef index, or ranks in the 65th percentile of the breed. Not surprisingly though, Iconic has a higher $B index. So he is that more terminal animal as compared to Converse, who had that more maternal characteristics in his DNA. So for this specific example, right, I would choose Iconic as the bull that I would select to AI my cows to, okay? So in summary, right, the biggest thing on how to use genomics is we have to define the breeding objectives. Understanding that it's not easy, right? You saw in the animals that I presented that the perfect animal doesn't exist. They both had their pros and cons for each situation. But we have to use the information that's available to us to make educated decisions on how those bulls fit into our breeding. And I didn't say this before, but let's say that heifer pregnancy, if I selected that first bull, he was a little bit low on heifer pregnancy. Maybe next year when I go to make my breeding decisions, I can focus a little more on heifer pregnancy and a little less on mature cow size, right? It's all about the balance and the ebb and flow of the selection decisions that you make, understanding that, there's never just one perfect end-all animal. And again, it's not perfect, right? Genetic variation will exist in every calf crop, and genetic merit is not everything. And what I mean by that is, if we go back to our first equation where we talked about the phenotype of the animal being a combination of their breeding value and their environment, there's a lot of different ways to look at this, right? There are some breeders out there who get good performance out of their cattle, but it's because of their excellent management, right? It's not because of their genetics. And then on the flip side, we could have producers who have good performance in their animals, but it's because they have excellent genetics and maybe some poor management that kind of the animals aren't able to phenotypically live up to their genetic merit for a trait. So for example, let's talk about heifer pregnancy, right? So if we have poor heifer pregnancy EPDs in our herd, but we have a really great fixed AI protocol where we sync the females or the heifers correctly, and we have a great AI technician, then we may actually get really good heifer pregnancy rates in our heifers for that year. But on the flip side, We have excellent heifer pregnancy EPDs for our herd. The genetic predisposition is there for them to get pregnant, but we just put them out with a bull, and or we have a terrible AI technician on the given day, we would still only see, that moderate good performance in the fertility rates and the pregnancy rates in that herd. What is important in the biggest return on investment for genomics is that you develop the excellent genetics, and then you develop the excellent management around those genetics to get the performance out of the animals so they can live up to their genetic potential. So, from a feed testing standpoint, right, you have excellent genetics for dry matter intake and average daily gain. You have really good feed efficient cattle. You have to match that with excellent rations, excellent feed testing, and just excellent management on the nutrition side to be able to get the true performance out of that animal. So because of time, I wanted to talk about a little bit more than that, but I'm going to end there today, and I will open it up, Becca, for questions.
Great. Thank you, Jamie. Thank you for your presentation and bringing it all together at the end, and how genetics and nutrition really work together. So we have some interesting questions. Do you want to throw up your contact information for anyone that would want to be contacting you?
I can just give it to you. My email is jcourter, COURTER, at Neogen, NEOGEN.com.
Right. So I'll jump into the questions then, and I guess I'll go ahead and share what our next upcoming webinar is in the meantime. So the first question, and we actually got two questions related to this. Let me pull. Oh, looks like I lost the chat, unfortunately. So is all about your accuracy. So the first question was, how does that improve as the number of progeny put into that number increases?
Yep.
And then the second question was, if you're seeing, like I kind of jotted a note, I saw one had 0.33 all the way to a range of 0.68. That would be between, around 40 to 60% accuracy. How do you address those types of concerns?
Yep. No. Okay. So for the first question, basically we refer to the benefit of genomic testing on accuracy as progeny equivalence. So let's just say for the Angus evaluation, we're doing parent averages, right? What a parent average equates to, the minute that an animal enters an evaluation and they haven't gotten a formal phenotype reported yet, that's when Angus will report that I, and then it's 0.05. So that's kind of the entering accuracy that some traits will have when they're just based on parent average, and that I stands for incomplete. Then as more information comes in and Angus kind of what we call turns the crank every week, that accuracy will actually tend to exponentially increase. So every progeny record that comes into play, as more and more comes in, that you'll see an exponential increase, and then you'll kind of see it taper off, where it's kind of limited by the heritability of the trait, right? So the more heritable the trait, which the more the genetics has power over the phenotypic performance of the animal, and the less of an influence the environment has. And so for carcass traits, they tend to be highly heritable, where there's a lot, we anticipate much higher accuracies as a result of genomics and progeny information, as compared to traits like heifer pregnancy that are have lower heritabilities, but they still gain value from progeny information. But a lot of times what we refer to genomics as is the progeny equivalent. So the minute we incorporate genomics into the evaluation, it's the same as if that animal had already had X amount of progeny. So in Angus, those progeny equivalents range from 8 to 33 progeny. So the minute that you add genomics to the evaluation, it's equivalent to the same increase in accuracy as if they'd already had 33 progeny. So basically, suffice it to say, and I think this kind of gets at the second question, a 30% accuracy is still really good. You know, that cap off, in my opinion, you know, unless we're talking about AI sires who have hundreds of progeny, we'll see them get kind of in that 0.8, 0.9 range. There truly are around like that 0.5, 0.65 area is where like we are very confident in the EPD that we're reporting. And again, the minute that you add genomics, that tends to increase that accuracy by at least 25%. We'll see that kind of jump. Did that answer both of them, Becca?
Yep, and then that was my question too, was how does the genetics increase that accuracy? So that's excellent, yeah.
Yeah, and it's different, again, based on the trait. So the more heritable the trait, the more benefit that you get from genomics because there's less environmental impact.
And do you guys at Neogen, or maybe some of the breed associations, do you guys put out the heritability of the traits?
I believe so. It probably takes digging, unfortunately. It might be easier to kind of get heritabilities out of kind of some peer-reviewed journal articles, but most of them will publish them either in like a yearly report, an annual report, or you may be able to do some digging and find them online. But overall, you know, like I said, carcass and growth traits, heritable, right? And then the ones like stayability, heifer pregnancy, they have a lot more of that environmental impact. They're going to be on that lower heritable side.
Okay, the next question we have is, I think the WW number and the YW are just a number, and you still have to compare it to whatever the association says is average. Still useful, not as dramatic, may have changed in the past few years, and is now based on 0 as the average. Not sure. I'm not sure what the question is in there.
So I think they're bringing up a really good point. The way that we use EPDs is to compare them to another bull of the same breed, right? So if you go back to, let's just use weaning weight as an example. I don't remember the 2 weaning weight EPDs of the bulls, but they were both Angus bulls. And so they're both being compared to the same average number. And no, it's not 0. It's whatever the average weaning weight, let's just throw out 500 pounds, right? 550. If that's the average weaning weight of Angus as a whole, then both of those bulls, because they're both Angus, are being compared to that number. And so what you would see is like if one was plus 50 and one was plus 100, then if I'm looking at those 2 bulls, then I would expect that second bull to have 50 more pounds of weaning weight on his offspring than the first one. So if weaning weight is something of importance to me, then he's a better bull for weaning weight. And I would anticipate that on average, his calves, if the breed average was 550, I would expect his calves to weigh 650 pounds on average at weaning, right? Unfortunately, because the way that the beef EPDs are reported, there's multiple genetic evaluations. So there's multiple, quote, averages. So if you're looking at a Simmental bull and comparing that to an Angus bull, they're not apples to apples, right? But beneficially, the USDA actually releases a cross-breed adjustment factors once a year. So at BIF every year, they'll actually report a table using their germplasm evaluation of herd of what they expect that adjustment to need to be. So, you know, it may be minus 20 pounds, you know, you have to take the Simmental EPD, subtract 20 pounds, and that's the true Angus EPD comparison, right? But they will publish a table every year to help with that too.
Great. Well, we are past 2 o'clock, so you've given us a lot to chew on, a lot of information. We don't have any more questions coming in. So thank you once again, Jamie, for joining us and for sharing very useful information with us. I just want to encourage all of you guys, this will be sent out and it will be posted on YouTube, of course. And then next month is going to conclude and wrap up this series. We're going to be talking with Dr. Genomically, veterinarian out in Kentucky, about some horse nutrition. So that should be fun. So I hope you all join us then. And thank you again to Dr. Korter.
Thanks for having me.